Lesson 5, demo. In this class, we sketch the graph of the derivative of a function with a given graph. We also explore what kinds of things make a function non-differentiable. We've got 2 demos and 2 activities today. Number 1, in the last section, we defined the derivative of the function f at x equals a to the f prime of a equals, and then there was that limit of the difference quotient. Now we can find f prime of a for every number a, and so we can think of f prime of x as being a function of x. So the limit definition of the derivative of the function, not just the function at a point, but the whole function is, and then you can see that this formula we had before has just become copied down below. The only change is that the specific number a, where we were focusing our attention, that specific number a has become a more general variable x. And so if you can find a derivative at a point, then we can generalize that and think about finding the derivative of a function at every point. So specific number a has become general variable x. Number 3, let's see if we can take the graph of y equals f of x pictured below and sketch the graph of y equals f prime of x. The basic idea when when graphing a derivative function is to plot points of the form x comma slope. So we'll say that again. It'll make sense after we do a few examples. Okay, we're going to pick some points that are on this curve. Now you can pick any points that you want to, but I have a specific way that I'm going to think about picking points. So I'm going to pick points that are at the highs and the lows. That is to say, points where the graph is flat. So I can see 3 places where this graph is flat. And the first place looks like it's at -1. And so if that graph is flat at -1, then the tangent line is horizontal. And the slope of any horizontal line is 0. And in fact, the slope is 0 for each of these 3 particular tangent lines. So we're going to start plotting points over here. Remember, the points are supposed to have the form x comma slope. So I'm going to copy the same x as before. So this x right here is -1, and then comma the slope 0. -1, 0 is the first point that I'm plotting over here. -1, 0. Same deal here, x comma slope. All right, looks like the x is roughly, I don't know, 1.2-ish. X comma slope, slope is 0. 1.2 comma 0 is our next point right there. And then the last one looks like x is just a hair bigger than 3, x comma slope, so a hair bigger than 3 comma 0. So that's our third point, maybe right there. Okay, and those 3 points have cut this graph into 4 pieces. So there's one piece to the left, there's this piece in between, this piece in between, and this piece to the right. 4 pieces. And all I'm going to do is pick one point in each of those 4 pieces. Doesn't really matter where I pick it. I'll pick this point right here, and I'll pick this point over here. Any point in between is fine. And then we are going to estimate slopes of tangent lines at those points. So I'm going to draw this first tangent line. It's that. Second tangent line, third tangent line, and fourth. Don't even worry about a straight edge here. This is just a very rough sketch. In fact, I'm not even going to do any numerical calculations here. This first tangent line, if I really wanted to calculate the slope, I would need to pick 2 points that are on the tangent line. So I don't know, I could extend it up here and extend it down there and say, oh, maybe that's a nice point with nice coordinates, and maybe that one up there. But I'm not doing that. All I'm doing is saying this tangent line first, is it uphill or downhill? This one's downhill, so the slope must be negative. And I'll say, is this thing steeper than a slope of 1 or flatter than a slope of 1? And we'll say this one is really steep, so it's got to be some number bigger than 1, except it's negative. So I don't know, -4, -5, wide range of answers are acceptable. I'm going to call this one here -4, the slope of that one. And so then, again, we're graphing points of the form x comma slope. The x that I picked was like -1.7, comma, the slope, -4. So -1.7, -4, something around here. Okay, let's do the next one. I used orange too much, so we're going to change to purple. Okay, so that slope right there, is it positive or negative? It's positive because that line is going uphill. And is it steeper than 1 or flatter than 1? This one looks like it's a little bit steeper than 1, but it's not as steep as the 4 that we just saw on the first tangent line. So how about we call it positive 2? If I estimate the slope of this one is positive 2, remember the points that we're graphing on the derivative to the right are of the form x comma slope. So the x is around 0.3 and the slope is 2. 0.3 comma 2 is my next point. 0.3 comma 2, something like that. Okay, let's do the next one. Too much orange here, so we're going to go right around here with blue. I'll draw a line. This one looks like it's downhill and roughly corresponds to the uphill purple one that we just drew. So can we just quickly call that one a -2? If you want to be really accurate, you can estimate coordinates of points that are on that line, but that's more than I need you to do here. So we're estimating the x and then the slope. X is around 2.4 and the slope is about -2. 2.4, -2. 2.4, -2, something like that. And then do I have any other colors? How about red? Okay, so we'll pick this one here. Any point to the right of that horizontal one. Tangent line, that one looks pretty steep. How about we call this one a slope of 4? Looks kind of similar to the orange one, just this one's going uphill. So estimate the x, estimate the slope. So the x looks like it's around 3.8 and the slope is around 4. 3.8 comma 4, something like that. And so now on the right-hand graph, this right-hand graph is supposed to be the graph of y equals f prime of x. And then we're just going to play connect the dots. So we just got to hit all these things here. Something like that. I'm actually going to exaggerate something. Let's try that again. So we come up here and then we go down and then we go up, something like that. And I just want to point out that the points that we happen to pick, like this purple one up here and this blue one here, are not necessarily the top or bottom points on the derivative graph. We didn't intentionally pick the steepest, the highest derivative point or the lowest derivative point. Those are just sort of arbitrary points in between the zeros, the horizontal tangent lines. Okay, so number 4, to reiterate, when graphing the derivative of a function, an x value is the input and the slope of the tangent line at that x value is the output. X comma slope. That's how you graph a derivative. Okay, based on the graphs above, let's guess the degree of f and then the degree of f prime. Okay, so f, if I count how many turning points it has, it's got 1 here, 2 here, 3 here. And we know that the number of turning points is at most 1 less than the degree. So if there's 3 turning points, then maybe this is a degree 4. It could be higher, but certainly it's not any less than degree 4. And now same game for f prime. F prime has how many turning points? I see 1 here and 2 here. 2 turning points maybe came from a cubic, right? I mean, it sort of looks like a cubic. So the graph of the derivative, the degree of the derivative is maybe 3. And we will soon see that for any polynomial f of x, the degree of f prime is 1 less than the degree of f. Taking a derivative of a polynomial brings you down 1 degree. You don't need to believe that at this moment, but we will see that it is true soon enough. Okay, so go ahead and do the first demo, and then we will come back. Sorry, not the first demo. Do the first activity, and then we will come back.